And the next comes Javier Fernandez from the fabulous UQ, crop physiologist and modeler. So we cannot wait for your presentation. Floor is yours.
Thank you. It was good that I was coming after Boer, so I don't need to introduce the topic. Yeah, we're going to stay in the same topic, and but we're going to switch continents. We're going to go to Australia. I'm going to be talking about the environmental characterization that we perform on variety trials in Invita project, this innovations in variety testing. So this is a sample of a good-looking variety trial, actually, for sorghum, but not all of them look like that, actually. And we need to see why and when that happens. And this is, well, you heard about the MBT network yesterday, actually, in one of the presentations by Vivi. This is a large network of about 600 trials each year, 300 locations, 10 species, where they're basically comparing variety performance, of course, and some other characters to compare the performance of these different genotypes, right? So what Invita proposed to use or to do is basically to incorporate digital technologies, particularly HTP technologies or environmental characterization, EC technologies, with different objectives. In this case, I'm going to focus on the characterization of what happens in terms of the environment and the main drivers of the differential ranking in the genotypes, and then in the analytics component of the project, which basically proposed to generate a scalable solution to then provide recommendations then for growers. Here, the main goal or the main objective is basically to characterize the main drivers of the GYE in these variety trials, to give the growers the opportunity to include the GYE also in the selection of variety when they're going to plant. So the first part of my talk is going to be about the data augmentation that we perform. We did quite a lot of work on trying to augment the data that is coming from MBT. So to start with the initial data set that we have, so this is basically the number of years, so 7 number of years for these wheat MBT seasons, 800 trials, over 4,000 trial by cultural combinations. And this is the basic information that we get, so geographical location management, genotypes, and of course, yield information. So on top of that, what we want to do is basically to augment with information coming from the climate, absence simulations as well, crop removal, and then I'm going to talk a little bit about the indices that we can get also from remote sensing estimation. In terms of climatic augmentation, I'm not going to stop too much on this, but basically we try to incorporate the main drivers that we expect are going to have an effect on the GYE, so temperature, water and humidity, radiation, heat stress, and frost. And in terms of the crop model augmentation, we basically are looking 2 main goals in here. One is obtaining good phenology information. So in that way, we can get accurate estimation of these phenological stages of the crop and then use the climatic indices based on the period of the crop. And we achieve a relatively good calibration of all the cultivars that we got, at least flowering date information using APSIN. The second component is basically obtaining additional environmental covariate that can explain some of the stress indices or some of the status of the crops in terms mainly on water status, nitrogen, and temperature. And for that, we develop a pipeline here to use satellite imagery to actually calibrate some of the environmental parameters, in particular soil, initial soil, water, and nitrogen condition. Using, in this case, you see this is the integration. What you're seeing here, this is the integration of APSIN and an RTM model, a ProSile. And basically, we're simulating a whole set of scenarios of initial soil conditions, and then we match that, or we try to minimize the loss function, basically, on the signal that's coming from the satellite. So the line here, the dashed line, is basically what's coming from the Sentinel. And then based on that, we calibrate these 2 environmental parameters. And then, of course, we validate this with biomass coming from the plots. We do the same, so that's one example of what we do in terms of satellite. We do the same, what we try to do to validate these models, because we think that getting good, accurate estimate of these environmental covariates is critical, basically, to then use that to explain the GYE. We do that with in situ sensors, for example, here cameras to separate the green area cover of the crop, and then also get a validation of green area index or phenology estimation, basically on the emergence of the heads. So for heading dates here. So for heading dates. And same here, an example for evapotranspiration in this case, where we are basically using that on the difference between canopy and leaf, air temperature and canopy temperature, we can get a validation of the estimation of ET, in this case, evapotranspiration. So that's a bit on the augmentation. Then we move on to the characterization. So we have these climatic indices, these stress-simulated indices. And now we want to define these envirotypes that can be used to explain the differential ranking. So one of the first question that we asked when we started was basically, well, we have this huge amount of information. Should we use it and there were discussion about this during the symposium. Should we use it as a static way via these stage indices, or should we use it as a type of functional EC using this in a dynamical way, right, the time series? And we tested this idea using different approaches here. So that was basically motivated because we saw in this case here in the right panel, you see this functional, well, when I'm referring to functional ECs, these are dynamic ECs, environmental covariates. These were actually quite reliable in estimating the trial mean, so the environment effect mainly. This is for yield, estimated on an unobserved year, trials in an unobserved season. And this is using climatic indices, and this is using, this is climatic plus satellite, and this is climatic plus APSIM. And they are relatively doing a relatively good job. So we wanted to do the same. Well, can we do the same, or does it make any sense to actually explain the G/E? So the four methods that we try are principal component analysis and penalized regression, both in their two options, I'll say, PCA on functional PCA, or penalized regression and functional penalized regressions. I'm gonna show you the example of the penalized regression, which were actually the ones that were working better than the PCA. This is an example of what we did. This block you're seeing here are lasso regressions performed on center blues for these genotypes, because now we're looking at we're trying to remove the trial mean. And then we're seeing which of the environmental covariates are the ones that are coming significant across them. And we performed this on a subset of genotypes that were actually generally repeated across our network trial. So these were about 50 genotypes that we did the same. And here you see the same for the functional regressions. So there are a slower number of covariates because now we don't have this separation of 4 stages that we defined in the previous step. So once we selected those potentially useful environmental covariates explained in the G/E, we then move on to the clustering procedures. The same here, clustering on the selected stage ECs or static ECs, or a functional type of clustering. And well, that's the selection here of the number of clusters that we need, or of envirotypes. But what we did is basically we wanted to compare this against a sort of benchmark for wheat in Australia, and we use the water stress environment types that were developed a number of years ago already. But this is generally a well-proven basis for defining water stress in Australia, based on 123 years of simulated data with these 4 environment types here. So that was our baseline comparison to say, well, are we adding anything with these new envirotypes? Here you have the interpretation. So at the end, we want to give this envirotype for growers so they can do something with this, so they can interpret. And this is how we did it. We normalized these environmental covariates. And then what you're seeing in red, it's basically the ones that are coming, that are in the distribution of these normalized ECs are basically are below the 20th percentile of the distribution. So we assume then that these are the limiting factors on each of the envirotypes. So for the envirotype 1, for example, here, you see that most of them are coming significant. Nitrogen here, rainfall and rainfall during grain filling. So we defined that as a water plus nitrogen stress condition. The second one was related to temperature. That was mostly associated with frost events, usually, and less frequently to heat event. Then we have water stress type and a no stress condition or more close to optimal conditions, mostly limited here by radiation in this case. So how did they work, or were they any useful? So for that, we used two criteria. One was the reduction in the G/E, using a baseline compound symmetry model, a baseline model with an additional G/envirotype term for using the reference drought envirotypes or water stress envirotypes, and then the ones that we are testing here. So I'm just going to show you for the method that performed better, which was actually the lasso on the static covariates, so on the stage covariates. And so basically the values you see here that approximate or in average, they represent about 20% of the G/E. So the reduction on the G/E was actually in average about 20%, which you might think it's not a huge amount of the G/E that we are explaining, but when you compare that to water stress types or the reference to water stress type, we're actually improving. We're going from a 5% being explained by the water stress type to a 20%, which is quite considerable. In terms of the cross-validation on untested trials, using our multivariate envirotypes, basically we have not a huge increase on performance, but again, was consistent in the increase compared to the baseline model or the baseline with the water stress types. But again, the question was, well, what does it mean for a grower, or how can a grower use some of this information? So we performed this kind of sort of a small example here, how the grower would use it. So imagine a grower on the next season trying to select the variety that they're gonna plant, and we perform this exercise of doing, well, the common approach is basically to go at the website and look at last year's season for their location, select the variety based on the highest performance and plant that one. Or the other approach was, well, what if you use the expected envirotype for that given location, for that given season, and select based on that. And we performed this across 3 years, testing on the next season, what happened after. And this show basically, a range of distribution, basically in terms of the difference between the selection of the method 2 here or method 1, but basically an overall mean of 2.2% in this blob difference if they were using envirotypes basically to select the variety. So again, these are promising results, at least to get a value out from this classification. So what we want to do next, or what we want to keep looking at, is basically expand this or go beyond the MBT, the trials, and go to farmer fields, basically using simulation in this case, to reduce the uncertainty of what would happen actually at the farmer locations. A huge, well, similar to what Boris presented for Europe, we had a huge effect on the year type, basically on the location by year effect. So the effect of the location was highly dependent on the year. So there is opportunity also to start looking at different classification of year types and include that in the definition of envirotypes. And this is an example that we perform not on simulated data. The idea is to do it on simulated, but we use it on real data in this case, where we basically are modeling using this p-spline model, where modeling the spatial distribution of the probability of occurrence of this 4 envirotype plus an additional one for abandoning trials. And well, that's the idea to then potentially classify or cluster these probabilities into fixed regions or fixed geographical regions that can be used. This is across dry years or wet years that can potentially be given to farmers to make a more easy interpretation of what they can do at their given location. And an example here is for this type of tool, where growers could potentially go and navigate through these, go to their location, and see what is the probability of occurrence on that. Again, this is just a prototype on the real data that we have, but it's something that we want to keep working on, even including potentially some opportunity for forecast models on reducing the uncertainty of occurrence for each of those environments. Last thing of what we want to keep looking at, and this is all part of a new, I have it in the last slide, but it's part of a new partnership, AGI, the analytics, Australian analytics for grain industry, which is all of these projects are going to continue in that big project, also led by Scott. And this is something that we want to look is go beyond the typical climatic or stress indices and now use satellite information to get responses to other environmental or even management factors. So this is an example of a biophysics-informed neural network that using high resolution or daily resolution climatic data and low resolution satellite imagery, we got a good estimation of biomass at a plot level scale, or if we're using reflectance or information coming from UAVs, biomass estimation at the plot level scale. And this is all trained on abscene data, on simulated abscene plus procile simulated data, but then tested on real data in the field. So again, as a summary, the envirotypes that we define up until here capture a greater proportion of the G/E comparison to the reference water stress types that we have in Australia. Again, there's a still amount of G/E that we're still not capturing. There is still significant, but again, consider that these are only 4 classes. So from there, you can go and even include the ECs within them. North and South regions were the ones that G/E was actually particularly influential. So in this region, it's potentially more useful to start using the environment for selection of varieties. And then the dominating effect of the L/Y is the positive challenge for these fixed regions. This is the analytics for the Australian grain industry project that I was mentioning, that most of these activities are going to continue in there. And then, you have my contact there if you want to reach out. And thank you.
Thanks so much, Javier. Yeah, I'm worried we don't have time for questions, so please catch Javier during the